Okay, well, let's continue with lecture 18, and we're going to be talking about discrete Fourier transform. Right? So we did the discrete Fourier series, which dealt with periodic signals. And what we're going to do is take a limiting strategy that if we have an aperiodic signal, we take it as a periodic signal with infinite periods. So how does that work? So here's the signal that we want with an infinite period. It just has 3 positive amplitudes here, and then it goes to 0. Now we could probably get this just by finding impulse response and doing this, but we'll do it this way. So here's a case where we have a periodic signal with period 5 that is equal to this signal on the closest 5 points to 0, but then it repeats, right? 1, 2, 3, 4, 5. Then it repeats 1, 2, 3, 4, 5, etc. All right. So what we're going to do is take this signal and pad it with more and more zeros until these other copies get pushed out to infinity. And what happens is when you push them out to infinity, you basically don't worry about that anymore. I mean, any system that you're dealing with, you'll be dealing with during a finite time. So as long as the mathematical description agrees with your signal over the time interval of interest, that's really all you care about. Right, so that's the strategy. Pad this signal with more and more zeros. Right? And you can go through, he talks about what happens. Let me describe in another way what happens. So the Fourier series represents a periodic signal. The Fourier transform represents an aperiodic signal, but they're both discrete in this case. They're both represented by spikes. So to get the Fourier transform, you pad the signal with more and more zeros to increase the period to n, where n becomes arbitrarily large. All right? Now, what happens when you increase the period? Well, you remember that the Fourier series, the number of terms in the Fourier series is equal to the period when we're doing discrete Fourier series. So as you increase n, the number of angular frequencies. But the maximum angular frequency remains the same. Okay, that's what we had before, we talked about aliasing. So the maximum angular frequency remains the same. The spacing between consecutive angular frequencies decreases. So you have basically have smaller and smaller frequency. Now, smaller and smaller frequency means longer and longer period. And since you're stretching out the signal by adding zeros, it makes sense that you're dealing with longer and longer periods, which have smaller and smaller frequencies. And the spacing between frequencies in the Fourier series is always even. So in this case, if we have n points and our maximum frequency is 2 pi, the spacing between the frequencies is 2 pi over n. And I'm going to define this number 2 pi over n as d omega n. Okay, and that should be suggestive notation. Right? As n goes to infinity, this is getting smaller and smaller. Okay, so remember the Fourier expansion equation, where the signal is expressed in terms of its Fourier coefficients here. There are n terms in this sum, big N terms in this sum, and we have this complex exponential here. So now, instead of writing a sub k, I want to work towards making this a function and not just a series. So I'm going to write this a sub k as a function of k omega n. It really doesn't matter if I write a sub k of a of k times d omega n. This should be, k times d omega n. Okay. Because there's a 1-to-1 mapping between the index k and the value of k times d omega n. You can define it either way. Again, I'm just trying to make a into something that looks more and more continuous. Now, the other thing is that k times d omega n is going to go from 0 to 2 pi. Right? Because the value of d omega n is 2 pi over capital N, and k runs from 0 to n minus 1. Right? So this argument in this function runs from 0 to 2 pi, whereas these coefficients, as n gets larger, these indices become larger and larger. So this is a way of limiting the argument or the domain of the function a. All right? And then this remains the same. I just simply replace the 2 pi over n with d omega n. And then we run this limit to infinity. All right, so you can get the more details in his lecture, but as n gets bigger, the spacing between frequencies becomes smaller. The values of these also become smaller, but there are more terms, right? There's more values. So this should be reminiscent of the passage from series to integral. We do this in probability when you turn a probability histogram into a probability density. Right? So we can write xn in this way. Now what I did was I put an n here and I put a 1 over n here. Right? So just multiplying and divided by the same thing. And 1 over n is just the same thing as d omega n over 2 pi. Right? Because d omega n is proportional to 1 over n. The constant of proportionality is 2 pi. Right? So we have this here. So we're getting everything in terms of d omega n and k times d omega n, which I'm going to change to a different variable. I'm going to call that capital omega. And that capital omega runs from 0 to 2 pi. And you see this is set up, if you remember how you went from sums to integrals back in calculus, you have a sum and you have this d omega term, this becomes naturally into an integral. Okay? So what we've got here is that this should be a small n, sorry, not a big N. And this is where the 2 pi comes from. If you go back to the formula, you'll find out that this is the Fourier transform expression. Right? So let me summarize the argument. The inverse Fourier transform, or of a discrete signal of infinite range, is computed as the infinite sum of terms. However, the inverse Fourier transform itself is defined only for frequencies between 0 and 2 pi. So this is a infinite sum to compute it, but the value of the function is only defined between 0 and 2 pi. And the Fourier transform expansion of a discrete signal is the integral over a finite range of frequencies. Okay. And this is because the frequency components are limited between 0 and 2 pi. Remember that why that is because of aliasing. So what we have here are basically 4 different variations of Fourier signal pairs. Okay. So first of all, we have discrete Fourier series. Now that's you're dealing with a discrete signal, so I should say discrete continuous signal. Okay, so it's a discrete signal. The domain is finite, so that means it's pure. You can think of that as periodic. So it's a finite domain. Okay, finite interval. Okay. Now, to compute the inverse Fourier, so here we can say, I can just call these the frequency components. Okay, so and then this Fourier, so I could say, this is going from signal, goes to the frequency components. Oh, sorry. Let's go back there. Signal to frequency component. To frequency components. Okay. And then the Fourier means goes from the frequency components to the signal. Okay. All right. So there are 2 ways to go. You can go from frequency components to signal. So to compute the inverse Fourier transform, you take a sum of a finite number of terms, and to get from the frequency components to the signal, it's still a sum of a finite number of terms. Right. Now, discrete Fourier transform, the signal is discrete, but the domain is infinite. All right. So the inverse Fourier transform is a sum of infinitely many terms. So this is what we saw. Okay, because you're summing over the infinite domain. Right, but the Fourier is an integral over a finite interval, and that reflects the fact that the signal is discrete. Okay, so discrete has to do with this finite interval, and infinite, of course, has to do with sum or integral of infinitely many terms. Right. Now, suppose you have continuous Fourier series, not a discrete signal, but a continuous signal, but it's on a finite interval. Okay, so in this case, to find the inverse Fourier components, you have to integrate over a finite interval. Okay, Okay, and then to find to get the signal itself, it's going to be the sum of infinitely many terms, because you're going to have infinitely many frequencies represented by this continuous signal. On the other hand, continuous Fourier transform, this signal is continuous and the domain is infinite, so you have an infinite integral to get the frequency components, and then to recover the signal you also have an infinite integral. So it's good to keep these in mind. I think he has an entire lecture on the relationship between these four. Right? All right, so slide 39 and 40, let's go there. Let's see where we are, slide 39. And this reinforces what I mentioned before, is that the Z transform is nothing but the discrete Fourier transform, but writing Z as e to the j omega. And that kind of explains the reason why the Z, when you do Z transform, the Z goes around a circle, basically. The important values of Z are the values of Z around a circle, because that's going to be related to these frequency values omega, because if I have a real frequency here, then e to the j omega is a point on the unit circle. So that's why the Z wraps around a circle, while the omega is a real number. Now remember, this omega has to be between 0 and 2 pi, so that fits nicely with the Z wrapping once around the unit circle. And that's a big reason why we use the Z transform typically rather than using this, because this only makes sense when omega is between 0 and 2 pi. So, all right. So he's showing the relationships between these. Notice this third row here. Basically, what he's doing is he's replacing Z with e to the j omega. Right? I think this is supposed to be a Z and not a S. But see, he just replaced the Z with e to the j omega. Here he replaced the Z with e to the j omega here. Now, this looks a little different, because here's a minus Z, dz x of Z. And here there's not e to the j omega out here. But if you use the chain rule on this expression, remember, you take the dd omega of x of e to the j omega, that's going to give you the derivative of x times the derivative of what's inside, which exactly gives you this. All right? So there's an exact correspondence between thinking about this as a function of Z and thinking about it as a function of a complex exponential. Right? So we have that. And then this here, it's interesting discussion. I can't say I really understand it very much. Here he's doing with video, with images what he did with audio before, trying to relate the Fourier transforms to what you see in the picture, and whether it's the magnitude or the angle that's important in preserving the feature. So you can follow his discussion here. I think it's very interesting they have these rays coming out. I can't say I understand why those rays are there. If I ever do understand that, I will try to explain it. And then here also, if you look at this, there's kind of this hyperbola where the phase is fuzzier than out here. This is more granular here, and this is more fuzzy. I don't know why that is. So that's also very interesting, but I don't understand why that is. All right, here again, you can see definitely there's kind of a band here where the phases are more fuzzy than out here, and they're more granular out here. I have no idea why that is, but there's always something more. And then this here is quite interesting. Here, look at the slanted pattern here. I don't know why that is either. There's a lot to discover and explore with Fourier transforms. It gives you a different window on the world. So thanks for watching.